Should we start? Yeah, okay, good. So Claudia de Rham, she's a professor of theoretical physics at Imperial College. She has taught in many places. She's originally and still Swiss, born in Lausanne, Switzerland, but Imperial College is in England. So she pretends she's English during the day, and at night she's Swiss. She is also a member of the American Academy of Arts and Sciences. She's won awards, but I think most interestingly, she works on gravity, cosmology, and particle physics and the intersection of those things. And one thing that she's known for is the idea that maybe the universe is accelerating in its expansion because gravitons, which are the particles that deliver, if you want, the gravitational force. We actually have never seen a graviton, but maybe the gravitons we've never seen are massive and not massless, and maybe that's why we see everything we see in the universe today. So that's a pretty cool theory. I wish I had had that theory, and I haven't. But I'm also not a theorist, but I'd love to measure a graviton. I'd love to have one in my house. Sorry, is this okay? Yes. So this is Claudia de Rham, but also we have another guest, which is Tasneem Zehra Hussain, who's here. And she will be joining us in conversation. She's a local, and she came to writing via theoretical physics as well. She was a string theorist from Pakistan, and she got her degree in Stockholm University, so she's also been in Sweden. And she's written a popular science novel called Only the Longest Threads. So she's exciting. She also writes for Nautilus, which is a great magazine, science magazine, and Three Quarks Daily. I'm sure you all subscribe to Three Quarks Daily. Do you want to write that down? Three Quarks Daily. It's I like quarks. Anyway, so we're going to have a lecture. Hi. We're going to have a lecture now, and then we're going to have an in-conversation, and then the cheese cubes come later. So thank you very much for coming. And
thank you. Thanks a lot, Vanessa. Thanks a lot. I don't think I can beat the humor in the introduction. That was the best part of tonight. So I'm going to talk a little bit about gravity, and I wish I could tell you this is me floating in midair, embracing gravity, embracing the beauty of falling. The reality is, typically when I embrace the beauty of falling, it looks much more like this. But if there's one lesson I'd like you to get for tonight, is that there is actually a beauty in falling, there is a beauty in failing, and there is a beauty in gravity, and that's what we are here to explore. Even though to explore this beauty, sometimes you have to go through experiences a little bit like that. So I'd like to start with thinking a little bit of what gravity feels like. We may think of gravity as something painful. We may anticipate how we're going to feel after the fall. But gravity in itself is actually quite a peaceful, quite an enjoyable phenomenon. So that person there is enjoying gravity. She seems pretty happy. If you imagine yourself orbiting the Earth, for instance, that person, that astronaut, is experiencing gravity, and that astronaut is experiencing gravity and is falling so freely without any distraction from any other forces that she's actually not feeling anything at all. But she's still very much experiencing gravity. Her trajectory is set by gravity, and yet she doesn't feel anything at all in that instance, because there's something very, very universal about how gravity affects us all, affects every single cell in her body in exactly the same way. And that's something very, very specific about gravity, this universality about gravity. Any other phenomenon, it affects different things in slightly different ways. And so that's why you may have some pushing or touring in your cells, and that's how you can sense other phenomenon. other forces in nature. But for gravity, because it affects every single cell, they're not discriminated, they're not pushed, they're not torn apart, and we feel gravity in no particular cell in our body. That in itself is a fundamental symmetry in nature. It's this universality of the phenomenon of gravity, and it's really what pushed Einstein to understand that if gravity affects every single one, whatever you are, in exactly the same way, then gravity can't just be a force that acts about two masses encoded in the existence of the masses themselves or the objects themselves. It has to be encoded in something much more fundamental, underlying nature of reality. And through a leap of, really a jump in this understanding, Einstein understood that the way gravity affects us all is encoded in the very fabric of space and time. Einstein understood, through Einstein's theory of general relativity, that masses, but not only masses, anything at all, any energy, anything present in the universe, affects the very fabric of space-time through curvature. And now we are all living on that fabric of space-time, so we're all experiencing this curvature, and that's how we feel the gravitational attraction. Now we understand that the larger the mass, for instance, the larger the curvature, and therefore the larger the gravitational attraction. That's a simple way to understand it, for instance. In fact, throughout the universe, everything, everyone, no matter who you are, wherever you are at any given time, we're all connected through the structure of space-time. We're all connected through this fabric of space-time, and therefore through its curvature, and therefore through gravity. In fact, the very notion of gravity, the very notion of curvature, makes no sense at one single point. The notion of curvature relies on connecting different points with one another. And it's in this connection between the points with one another that gravity and curvature manifest itself. This may seem like a simple play, but actually it's something very concrete. And for us, living on a curved surface of the Earth, this experience should be actually quite tangible. We all understand that we're connecting different points on the surface of the Earth. And it may seem like, from the outside, that those connections are curved, but those are just straight lines, adapting for the curvature of the surface in which we live in this case, the surface of the Earth. So we can think of gravity, we can think of space-time as a patchwork of events, a patchwork of points, and gravity is the thread connecting them all together. Once again, you may have the impression that this is just a cartoon picture that we're drawing for the public, for you to understand, but actually this is something very precise, that we can make extremely precise. This is the most precise phenomenon that we know and that we can measure. In fact, this connection in the different points in space also works in space-time. And so as we are connecting at different points in time here on the surface of the Earth, for the satellites on orbit above our head, the way they connect the different points in time is ever so slightly different as compared to us. Because the curvature up there is ever so slightly different as compared to us in here. And so that means that the way we experience the flow of time, right here, right now, is ever so slightly different as compared to what the satellites on orbit above our head are experiencing the flow of time. Now, of course, this difference is very, very small. Within a minute, there's just a few dozen microseconds difference between the two. But in that time difference, light can travel 30 centimeters. So that means that within this talk, by the end of it, and when you have cheese, etc., the difference between our flow of time for us here and for the satellites will be half a mile. This is enormous for light. This is huge. And we're using the satellites, for instance, those ones, our GPS satellites, to understand our positioning here on Earth. And so we really need to understand gravity. We really need to understand how to connect points in space and time together to understand where we are, what we're doing. And if we need to go to this level of precision to understand the reality of what we live here on Earth, just imagine the level of precisions we need to go in our understanding of space-time, in our understanding of gravity, if we want to understand our place in the whole universe. And that's what I am interested in as a cosmologist. I want to understand our place in the universe. And so for that, we may zoom to the largest possible distance scales that we can imagine. So let's imagine we're zooming out of the solar system. We're zooming out of the galaxy. We're going to zoom out. This is just an animation, of course. We're going to take a little trip over millions of years, millions and millions of years, out of a local cluster of galaxies and over distances we span over thousands of millions of kilometers apart. Now, what you can see in here is just an animation in fake color. In blue, animation of filaments of dark matter. Those are fake colors. We don't see dark matter because it doesn't interact or doesn't interact much at all, doesn't interact as far as we know so far with light or with anything that we know of apart from gravity. But we know it is present because of its gravitational effect on everything else. And at the core of these filaments of dark matter, they are the clusters of galaxies in which we live in. Now, if we look at objects on those distances, what we see is that the further away we look, and the fastest objects seem to be moving away from us. And so that doesn't mean that we are living in a center of a universe, but rather what it means is that space itself is stretching. We're living in a universe which is expanding, as you may have heard. So the space between any two galaxies, any two clusters of galaxies, is expanding. And so the further away you look, the fastest things seem to be moving away from us. But now we all know that even though gravity is a very weak phenomenon, it is an attractive phenomenon. And so it attracts masses together. And so even though there may have been a big bang, starting with what we can think in our head as a big explosion, pushing the expansion of the universe, we would have expected the mass of all of the filaments of dark matter and the clusters of galaxies to attract themselves gravitationally and to lead to possibly a slowdown of this expansion, or even to the point where this expansion of the universe should come to a stop and would lead to a contraction of the universe. That's what we would have expected if it were true that most of the energy present in the universe was confined in what we can see through our instruments, those clusters of galaxies confined within the filaments of dark matter, which we can't see directly with light, but we can see through the gravitational pull. However, over the past 25 years, what has been observed is exactly the opposite. The expansion of the universe is not slowing down, it's accelerating, is going faster and faster. And that even dark matter cannot explain. And that is contrary to what we would have expected, once again, if it were true that most of the energy present in the universe was confined in these filaments of dark matter, which I'm accepting is present, and these clusters of galaxies. So to understand whether this is really the case, we could zoom into what we call a cosmic void, one of these completely empty regions of the universe, completely empty out of anything at all. There wouldn't be any dark matter in there. There wouldn't be any galaxies. There wouldn't be any black holes. There wouldn't be any dust. There would be absolutely nothing tangible at all. Those cosmic voids are millions of light years across. Just imagine how lonely you'd be in there. There'll be absolutely nothing. And yet, even in the middle of these cosmic voids, you wouldn't be completely alone. Even in empty space, out of nowhere, is still filled with some quantum vacuum energy, which you can think of as the soul of all the particles that you know exist. Those quantum fluctuations are there for all of the particles that we know exist and fill every pocket of the universe. They are not tangible per se, but they're still quantum energy that is present. And in fact, the discovery of the Higgs and the Higgs mechanism is the proof that empty space is not completely empty of energy. It's at the very least filled with the energy of the Higgs bath, which is what gives a mass to the other particles that we know. And so if we now take Einstein's theory of general relativity, which explains how anything present in our space-time leads to curvature, and we add this quantum vacuum energy of particle physics, it leads to an accelerated expansion of the universe, in some sense exactly as we observe. The only difference is that the expected rate of acceleration of the universe due to this quantum vacuum energy is too fast. And it's not too fast by just a factor of 2 or something I can just forget. It's too fast by at least 28 orders of magnitude. This is a little problem. And so you may have heard the story in quite a different way. This quantum vacuum energy problem is so puzzling that we typically phrase it in a very different way. We typically phrase our problem in cosmology in the sense that most of what we are, all of the normal matter, let's call us normal kind of matter, you and me, and even black holes, and even light itself, if you want to, doesn't lead to much. That only leads to 5% of the energy budget of the universe. Then there's a larger proportion, which is dark matter, which is not made out of what we are, but still some matter which we can understand the characteristics. And the rest is what you may call dark energy, which drives the accelerated expansion of the universe. And you may have heard that we don't know what this dark energy filling the universe is. And you may ask yourself, why is the universe so dark? But the real question isn't, why is the universe so dark? The real question is, why is the universe not much, much, much darker? Why are we so fortunate to live in a universe where we're not completely dominated by this quantum vacuum energy, which would stretch the very structure of the universe apart? How come this quantum vacuum energy that should be filling every pocket of the universe doesn't lead to much more in the energy budget of the universe? So what went wrong? If we take Einstein's theory of general relativity and we add this quantum vacuum energy, we will lead to a way too large effect. Should we abandon this idea of the quantum vacuum energy? And that's actually what is typically happening when we postulate the existence of dark energy. We just ignore this big elephant in the room, and we postulate instead the existence of a new kind of energy, which, ta-da, would lead to the accelerated expansion of the universe. Well, we're not addressing the problem at its core. Is it instead Einstein's theory of general relativity that breaks down? We don't know. But we can contemplate for a second this possibility. In Einstein's theory of general relativity, we say that gravity has an infinite reach. It never stops, technically. Even though it decays as a Newton square law over distances, it never really stops. There never is an end to it. So that means that if you take two galaxies located on the other side of the observable universe from one another, that's 10,000 million trillion kilometers away from one another, they would still technically exert a small gravitational attraction in each other. But that's not really the problem. The problem is that in order to understand the dynamics, you also need to account for all of the quantum vacuum energy that fills every pocket of the universe in between. And that's what leads to this quantum vacuum energy problem. So you can instead consider a possibility where, rather than having an infinite range gravity, you could have a model of gravity which looks like Einstein's theory of general relativity for most of the region in the universe, but after a while, it's just becoming lazy, and it just stops. In that case, we'd have a theory of gravity, which is a finite range gravity. In fact, that possibility that gravity could have a finite range is a very natural one that has been postulated by many different scientists throughout the centuries, more recently by Salam, who was Nobel Prize winner from Pakistan. But that possibility was always refuted until we find a way to make it work. So I don't want to go through the knobs of what it means to make it work, what a theory of massive gravity is in practice, but what I want to show is, in a second, how we could actually observe it with future experiments, with future missions. And for that, we need to go to gravitational waves as an example. We know that when two black holes, for instance, are merging, they distort the fabric of space and time around themselves so much that they produce gravitational waves. And those gravitational waves are then traveling through the ages of the universe, reach us here on Earth. They form space through our instruments in a way that we can actually detect it. And on the top left is the first direct detection of gravitational wave signal that has been observed in 2015, announced in 2016. And when it was announced, it was declared that this was the irrefutable proof that Einstein was right. Of course Einstein was right. Well, Einstein was right with so many things. But in fact, the best feature of his theory of general relativity, is not that Einstein was right. It's actually, we know from the outset that Einstein's theory of general relativity predicts its own failure. It predicts its own failure through the Big Bang, through black holes, and possibly there's other failures of Einstein's theory of general relativity that we may be able to observe. For instance, if gravity had a finite range, that would also mean that gravitational waves, as you look at them at very, very small frequencies, or a color that would be very much towards the red, in terms of analogy with light, they would travel ever so slightly differently as compared to the other gravitational waves, and the signal that we would observe at very low frequency would be ever so slightly different. So with future missions, for instance, the LISA interferometer, which is a space detection of gravitational waves that will be sent in the 30s, hopefully, we're hoping to being able to observe gravitational waves with the smallest possible frequency and being able to determine whether or not gravity has an infinite reach. Whether or not the theory of massive gravity, of finite range gravity, will survive those to test, that's for future generations to tell. But the beauty is that the possibility now exists. And the beauty for me is that it really allows us, through those gravitational waves, to being able to connect the infinitely small, some quantum vacuum energy, which fills every pocket of the universe with the largest possible scales of the observable universe, and anything in between. So I think this is a good time for a discussion now. Thank you.
So this is working, right? Yes. Okay, thank you for this absolutely wonderful talk, Claudia. And for the fabulous book. I love the voice in it. It sounds so much like you. There's so many things about science, but also a life in science. So when you read it, you'll get a wonderful combination of research, but also what it's like to actually be a scientist. I have a ton of questions. I don't think we have enough time to get through half of them. But I want to start with the question I had even before I read the book, from the title itself. It's a very sort of counterintuitive title. I read it and I thought, what does she mean by that? What's the beauty of falling?
Yeah, thank you for the question, and thank you, Tasneem. There's a play of words in different ways. The first thing is exactly what you say. It's not beautiful to fall down. It's quite the opposite. And I want to take apart this idea that falling is something negative. It's actually something which is beautiful in itself. If you embrace it, if you let yourself go to it without the fear of the anticipation of what will happen afterwards, it's demystifying a little bit this fear of falling, and sometimes this fear of science, in some sense, that some people have. So there is the beauty of embracing the fall itself, because gravity is in itself very beautiful. It's only when you fall, when you reach the ground, that it may be a little bit painful. But if you imagine yourself, as I had at the beginning, someone in free fall, there's something very beautiful in this experience. And sometimes we need to extract ourselves from everything else to really appreciate the beauty in that experience. There's a play in the fact that I talk about my own failures and how those are not embarrassment that I should just forget about. It's actually what has led me to where I am right now. And so this failure, there's a beauty in it, and there's a failure in every scientific processes. Even Einstein himself, any scientist that you know will have gone through loads of different falling and failures. And those are things that we need to find beauty in them because we learn from that. That's where we are. That's why we are where we are right now. Of course, the finality is the beauty of the failure of gravity itself. Einstein's theory of relativity does fail, does fall down at some point. And that in itself is something which is fundamental. It's really a privilege to know that a theory will fall down, will fail, because then we know where to look for new signs of new physics. This is something actually quite astounding, that a theory comes in with its own flag telling us, this is where I fail, this is where you have to look for new things. For me, this is really amazing to have such a theory.
That's one of the things I loved about the book, is that it works on so many different levels. There's science, there's sort of philosophy, there's life lessons, there's so many insights that you get. One of the things that you wrote that I'd flagged is you wrote, as we embrace gravity, we can't help but also pit ourselves against it, leaping, floating, or flying as we pursue brief moments of freedom from its command. Now, one of the things you will find out when you read Claudia's book is she's had a fascinating life, and she really has explored gravity in all of these ways. So she's been diving and experienced what it's like to be almost weightless in the water, or sort of while she's diving down. For flying, she went and got a pilot's license, and the big story was that she was training to be an astronaut. So the ultimate thing was experiencing weightlessness in space. And there was a slight technicality, nothing that she did, but there was a slight technicality that prevented that happening. But I think it's kind of interesting that the way, you wanted to escape gravity's clutches, I think you said, in these ways, but the way you might end up doing it is completely different. I mean, you might end up escaping it by showing that gravity's clutch isn't infinite. So could you just give us a little bit more about that theory and how it happens? You talked about how a graviton could have a mass. But before, we weren't able to go into that completely. And I think to understand what the ramifications are, it would be good to maybe talk about briefly what a graviton is. And maybe in analogy with a photon, you have this really interesting thing in the book where you draw an analogy between electromagnetic waves, which are a lot more familiar because it's light, and what you call glight, which is a term I loved. So could you explain a little bit more?
Yes, absolutely, yeah. And I think I love what you're saying, because it really shows a little bit of how nature is teasing with us and throwing curveball at us. And it's for us to make sense of that and make progress in whatever nature throws at us. For gravity, for the graviton and the analogy with light and how we can go and understand it at a more fundamental level. Actually, I have a picture. This is a fake picture, of course, of a graviton, but what do we mean by that? I think it is useful to go back to gravitational waves, which seem very abstract. We have detected them, but it's not something that we are used to in our everyday life. We're not going to feel gravitational waves there. We really need, it took us 100 years, actually, to perfect instruments to just being able to see the first shed of gravitational waves passing through. But there's a very similar analogy with another phenomenon which we are much more used to, which is light. Light is produced with shaking, not black holes per se, but shaking charges with respect to this phenomenon. Light is associated with electromagnetism. Light is an electromagnetic wave. So now that's a very technical term. We prefer calling it light, but it is some shaking of an electromagnetic field. And so to produce light, or to produce these electromagnetic waves, what we need to do is shake around some electric charges, for instance. So in a bulb, you take electrons and you just shake them around, and they radiate. They just emit electromagnetic waves. They emit light. We're used to this, and we observe it, and we've been communicating actually with each other. We've been communicating with the rest of the universe through light since the beginning of humanity, actually. Now, when it comes to gravitational waves, when it comes to gravity, it may seem that it's something so very different. And often we play on the fact that gravity is not a force, it's a different phenomenon. It is just the manifestation of the curvature of space-time, which is true, it's absolutely true, but it doesn't mean that gravity doesn't also tease us in some sense and doesn't also have a representation which is very similar to what electromagnetism has. Actually, Salam, the picture of Salam that I had in the board, he was one of the first to understand that different fundamental forces of nature are related to one another and can be unified to one another. He did that for the electromagnetic force and for the weak force into the electroweak phenomenon. And nowadays we believe that all of the forces of nature, including gravity, should be unified into one underlying framework. And actually your work has been done working on some of those aspects. Now we know, for instance, for light, we know that we can describe it as a classical system, which are electromagnetic waves. We understand that very well. But we also know that fundamentally light is being carried by quanta of energy, which we call the photon. At the fundamental level, light is a quantum phenomenon. And so we can think of it as if we take light of a particular color or a particular frequency, and we reduce its intensity, we'll see that at some point we can have a given energy of light in that frequency, or double that energy of light, or triple that energy of light, but nothing in between. And so, for instance, electron can absorb that particular amount of energy, but not anything in between. Light is quantized. There's a discrete amount of energy being present in light that we observe, which is through the photon, the particle of light. And exactly the same thing happens for gravity. So the gravitational waves, we just detected them after 100 years of the postulation of Einstein's theory of general relativity. We finally just detected gravitational waves. But if we want to make sense of gravity with everything else, with the fact that it connects to the other phenomena in nature which are themselves quantum, then it has to be the case that the gravitational waves themselves, they are quantum in nature. So they are carried by a quanta of energy. Of course, a quanta of energy is very, very small. The gravitational waves that we have observed have a lot of this quanta of energy, so it behaves like a classical system. But fundamentally, they are just carried by individual gravitons. A lot of them, but if we were able to reduce the intensity of those gravitational waves sufficiently, we'll see that you just have one amount of it or twice that amount of it. And that amount, that quanta of gravitational waves, we call it the graviton. So there's a fundamental particle that carries gravity, which is a graviton.
So your own work has basically dealt with what would happen if a graviton had mass. And you mentioned something about how general relativity predicts its own, I wouldn't call it downfall, more like where its limits are. It says, I'm only valid till so far and no further.
That's right.
Which I think it did in what you call a very humorous way, which I like, because it's almost, so general relativity predicted the existence of black holes, which basically means there's a singularity. So there's a point where space and time almost collapse. And because it is about the curvature of space and time, by definition, it doesn't work there. So it's almost like this circular thing. General relativity says there will be singularities, and when you reach the singularity, I will then break down, and you can't depend on me anymore. And most people, when they're confronted with that, then go down that route and say, okay, well, what happens there? What happens when space and time is that small? It's all about the singularity. It's all about quantum gravity. What I found very fascinating with you was that you said, so it doesn't work there. So where else doesn't it work? So instead of going to the smallest, you went to like the largest scales possible. And can you tell us what would happen there? I mean, if a graviton had mass, how does that affect the large scale?
So yeah, that's an excellent question. Maybe to draw an analogy there as well for us to represent it. we can draw the analogy with the weak force. I talked about electromagnetism. We all, hopefully, we're used to this phenomenon. We're used to the electric force. We're perhaps not as used to the weak force. The weak force is, again, one force which was unified, thanks to Salam, Glasha, Weinberg, into the electroweak phenomenon. It is actually very, very similar to electromagnetism, to electric and magnetic force. Simply, it's weak. And the reason why it's weak is because the fundamental particles that carry it, they're not called the photon, they're called the W and the Z bosons. Okay, they don't have very interesting names, but they're carried by fundamental particles as well. Those fundamental particles, actually thanks to the Higgs mechanism, they carry a mass. They have a mass, they are massive particles. And so this mass, in some sense, that's not exactly true what I'm going to say, but in some sense, it impinges the propagation of this fundamental force, the weak force. And so that's why the weak force only operates in subatomic scales. Beyond that, we don't experience the weak force because it has switched off a little bit like I'm drawing in over here. So the blue curve there, don't think of it of gravity. Think of the pink curve as being electromagnetism and the blue one as being the weak force. So those are two forces of nature which are unified. We understand how to combine them together. But just the fact that the particle that carry the weak force massive means that the range of the weak force is actually limited. It has a finite range as compared to electromagnetism. So if you were very, very much inside an atom, you would be able to experience the weak force and the electromagnetic force. But when you go to larger distances, you only experience the electromagnetic force. Now, I want to draw the same analogy with gravity, but of course, we can't say that gravity only operates on subatomic scales because otherwise nothing would have get formed in the universe. So we need to scale that up to much larger distances, to a fraction of the observable universe today. But then otherwise, the idea is very much the same. Everything in nature, everything in theoretical physics is very simple as concepts, as idea. So the idea there is to borrow the same thing as compared to what nature has already given us. Nature has already shown us that you can have a force in nature which is limited in its range because the particle that carries it is massive. And so a very natural question, it's a very actually natural question in itself, separately from the quantum vacuum problem in cosmology or anything like that, is to ask ourselves, is the fundamental force of gravity carried by a massless particle, like we think the photon is, or is it carried by a massive particle, like we think the W and the Z boson is? And that would limit the range of the gravitational force if it had a mass.
Okay, so let me just get this straight. You're saying that gravity waves are made up of gravitons, just like electromagnetic waves are made up of photons. And light has this infinite range because the photon is massless. But the graviton, because it has a mass, and I'm assuming a very, very, very tiny mass, right? Because we do know that gravity waves travel at almost the speed of light.
That's
so
right.
It has to be a very small mass.
That's right.
So it keeps it from being infinite, effectively. So
the range of gravity. That's right.
Infinite.
That's right. That's right.
So, but it's a very, very small mass.
That's right.
What exactly does that have to do? How does that play in with dark energy?
Excellent question. So a very natural candidate for dark energy is this quantum vacuum energy. We would expect it to be present because that is a natural element of particle physics. We have every element of it. We should have a quantum vacuum energy being present. The estimations, however, from particle physics is that the amount of it will be way too large. And so it's not like it wouldn't be sufficient to explain the accelerated expansion of the universe. It would be quite the opposite. We'll have far too much of it. And so the issue is that we have too much of a good thing in some sense, so much so that it would completely stretch the space apart. We wouldn't be able to live in this universe in any way. And so this is where this finite range gravity comes in limiting the effect of this quantum vacuum energy. rather than saying this issue is so big, it's so much in our face that we don't know how to deal with it, we're going to accept it. We're not going to set it apart and postulate the existence of a new kind of dark energy. We're just going to accept that this quantum vacuum energy is present, but we're going to change the way it affects the universe. We're going to change the way it communicates its influence on the rest of the universe through gravity by changing the mediation, by changing the messenger, and the messenger is gravity, is the graviton. That's what we do.
I have a ton more questions, but I think it's time to open it up to the audience and let them get something in if they want. And if not, I have a list. Oh, there.
Thanks. I have a question. So just to understand.
We want to hear your question.
Oh, I'm getting loud enough. Thanks. Thanks. Yeah, so in terms of understanding your idea, so the idea is that, so if you assume that gravitons carry the gravitational field, then are you able to get the inverse squared law, or is it that it actually falls faster than squared? So it's like 1 over r2 plus epsilon. Is that the idea, or?
So
that's why you get the acceleration in like really large distance.
So let me just say, Einstein's theory of general relativity, we typically describe it as the curvature of spacetime, but already there, we have all reasons to believe that it's carried by gravitons. So this is something which has been known for almost a century, actually, not quite, but there's not really any issue in thinking that gravity is being carried by quantum particles, which are the graviton, and it matches perfectly. So there's no issues there. And in some limit where we should recover the Newtonian approximation, for instance, we will recover this Newton's square law as Einstein's theory of general relativity also gives us. So that all matches up perfectly. Now, the only difference in what we'll try to explore, and this is an exploration. We have to understand, I'm not postulating this is reality, end of story, let's move on. This is a postulation. We need to explore things around. We need to see what would happen. So what would happen if the particle that carries the gravitational phenomenon had a mass, so you had a massive graviton as opposed to a massless graviton, as would be the case in Einstein's theory of general relativity, is that in the same approximation, the force of gravity would then decay not as in the square law, but an additional exponential suppression. So in that graph, the square law is already accounted for by saying that it's times the area. So over some range, it will look like it's a square law, and at some point, that will switch off completely. Yeah. So you will have an exponential suppression at some point. We call that a Yukawa suppression, if you like to. That's just a name. And that we do observe for other phenomena, like the weak force. We know that some forces have a Yukawa suppression, like so.
Yep, thank you.
Maybe I can just. We've got one over here, and then you got over here first.
It looks like, oh, I'm sorry. It looks like in your graph that the finite range gravity drops off abruptly rather than gradually. Do you have an explanation for that?
So yes, this is a, I have to say, this is a picture, right? This is not something we can follow through, and that has to happen in a limit. We can see how it works, but when we're dealing with cosmology, it's not the same limit, so it would be slightly different. But here, the force is multiplied by the area, so you still have the inverse square law, so it's still at the force of gravity as you go to further and further away distances. You feel it less and less, just as it is in Einstein's theory of relativity. But then when you reach distance scale, which is related to the scale in which gravity has a mass, then it can't propagate anymore. It's just like it stays put. And so you have a sharp transition at that point in the sort of weak gravity approximation that we're dealing in here. So we know this happens once again, we know this happens for the weak force. For instance, we know for the weak force has a transition where we don't see it at all. It's sharp beyond it's very small scales, but beyond subatomic scales, it just switches off completely. Yeah, and we don't experience it otherwise. It really need to go to very, very small distances to being able to experience this weak force. So it's all about the existence, the competition between the different scales being present in the system.
Does this work? Yes. So the relationship, I'm a little, the question is around the relationship of gravity to the quantum vacuum energy. Is it that we do not experience that quantum vacuum energy beyond the cutoff of the gravity? In other words, we're isolated from all of the quantum gravity that's beyond the finite range of quantum energy beyond the range of gravity. Is that and is it the volume of quantum vacuum energy that we experience, but beyond that we would not experience it? And if this is the case, have you made some estimations of the mass of the graviton and the amount of quantum vacuum energy?
Yeah, so very good. The beauty of this is that it's easier for me to, in a picture, to show you in terms of the volume. Seems to be more intuitive, or maybe it's not, I don't know. The reality is that we're dealing with a theory of space-time still, and so anything that has an effect in space also has an effect in time, and it is the time aspect of it which is the essential in here. So it's not so much that, a little bit, but not so much that the quantum energy of the vacuum only has an effect on a finite volume in the universe, and beyond that, gravity doesn't feel its effect. It's more so, the crux of the matter is more so that the effect of the quantum vacuum energy dies off over time, of a sufficiently long period of time. And because the universe is so old, we are finally reaching the time in our universe where this effect of the quantum vacuum energy is dying off. This is more what happens. For this to work out, we would need the mass of the graviton to be related to the age of the universe. And that's precisely the order of magnitude as to what we want. And that in itself, you can think of it also in there, the age of the universe and the size of the universe, that leads to roughly the same scale for the mass of the graviton. That's the scale that we need to have for the massive graviton. So then, once you have that, you can ask yourself, is that consistent with the effect that mass of the graviton would have on the signal from gravitational waves? At the moment, we're still 10 orders of magnitude away from that, so this is completely consistent so far. It's also completely consistent with, as Tasneem was saying, we know that the gravitational waves are traveling very, very close to the speed of light, in 1 part to the 10 to the minus 15, so very, very close to the speed of light, 1 to the 10 to the 15, sorry. But these are at a particular frequency. And so with the future experiments, we're hoping to detect gravitational waves with a much lower frequency and much more precisely, and so to put a constraint on the mass, which would be closer to, as compared to what we would expect it to be.
Sorry, a naive question. Given the equivalence of gravity and acceleration, does the quantization of the graviton imply a quantization of possible accelerations?
So that is for a particular frequency, right? For a particular frequency, the amount of energy you have in gravitational waves is quantized. Now, the connection with the acceleration in itself, this is a classical effect. You're not dealing as much with a frequency of gravitational waves when you think of it like this. But to answer your question, yes, fundamentally everything is quantum. So you can think of the effect that gravity would have, that you can think of it as an acceleration, or you can think of it as an amount of energy carried by gravity. This would all be quantum fundamentally, yeah.
One and the other. Oh, thank you. Sorry, just this man and then you.
Hi, can you offer some comments on the two postulations? The accelerating expansion of the universe that we currently have observed is because of the inflation at the beginning of the universe. Is it possible or is it flatly wrong? Second, the issue of a varying speed of light, which says at the beginning of the universe, the speed of light was faster than the speed of light it is now. Well, is there any fundamental reason to assume that the speed of light should be the same throughout the evolution of the universe, or is it possible in the future it could be different from it is now? Thank you.
Yes, so I can give you a little bit my perspective about both of them. So for the first one, indeed, there was a period of, we believe there was a period of accelerated expansion at the beginning of the universe, which is inflation. The scale of inflation, the scale of this acceleration is very different as compared to the scale of the accelerated expansion we have right now, of the order of 120 orders of magnitude. So in principle, I can just write down a theory very easily where I say it's just a continuation from one another, but the scales are so different that you need to understand that with such a high level of precision that it's too much to ask for the same phenomenon to remain the same of such a large range of scale. So it is something we can very easily write down, but to really prove that there's a connection between the two of such a large amount of scales, it relies on us being extremely precise on all the experiments that we can have. I don't think we are at that level of precision at the moment. That is a little bit my perspective on this. The scales are so different that it's hard to actually trust them throughout the whole range. Now, in terms of the varying the speed of light, actually, I have colleagues that work on that. I don't work on this myself. For any varying of the fundamental constants of nature, being the speed of light, being the Newtonian gravitational constant, or the analog of that, you can think of those variations as being carried by another field, and you can actually put constraints on how much there is a variation of all of these phenomena throughout the ages of the universe, and also through different environments. It could be that those constants of nature, being the speed of light or the gravitational constant, is environment dependent and not just time dependent. But we have very strong constraints on that as well. So at the moment, we know that the fundamental speed of light in the vacuum has to be very close, actually, very close to constant throughout the ages of the universe, because we have different probes of different phenomena that rely on the speed of light through different ways.
Thank you for a really interesting talk. My question is that other people have tried, before your work, have tried to make massive gravity theories work, and they always tossed them out because of the fact they couldn't get around the existence of what some people, I guess, call ghost particles, which
That's right.
have totally unacceptable physical consequences.
Yeah.
Can you talk a little bit about how your theory makes the ghost particles vanish, so that you have a theory that doesn't have obvious unacceptable dimensions to it?
Yeah. So that was exactly the crux of the matter. I think you know exactly what was happening. Actually, Pauli, I just put the picture there because Pauli was one of the first ones that realized that you needed to have a very specific structure already for what they would call Fierz-Pauli, the linearist version of massive gravity, so that these ghosts would disappear. And then throughout the past century, then people thought that as soon as you try to implement that in a more fully fledged theory of gravity, you are led to some ghosts that are always present. And I think I like everything you said, Tasneem, because it really also shows how sometimes nature teases us, but also sometimes we observe something and we sort of put everything back in the same context, in the same patterns. And we have to escape that to being able to make progress. So it was true that throughout the 70s and the end of the last century, it was believed that every time you have a theory of massive gravity, you are led to those ghosts. But the way this was realized was always following the same recipe. And so it's a self-fulfilling prophecy in some sense. And people were trying to do different things, but in some sense, they were always trying to do the same thing and ending up with the same results. Though I can tell you, I can show you exactly what went wrong, but what I can tell you is that it was almost a matter of luck that we weren't trying to deal with a theory of massive gravity in the first place. We were trying to deal with another theory based on extra dimensions. There was gravity with extra dimensions, so following the same symmetries as gravity. But from a four-dimensional perspective, when we project it in 4 dimensions, in some limits, it looks a little bit like massive gravity. But basing ourselves in something which was just general relativity in higher dimension, we were protected from any ghost instabilities. And yet we could see that we were led to something that looked like a theory of massive gravity from 4 dimensions. And I thought for a whole year, I thought that there was some mistakes in what I was doing. It was almost by accident that we ended up in a result where we finally saw how we could evade all of those issues. So that requires, in that case, by accident, finding yourself outside of the box, outside of the framework. And once you see that, you say, of course, we could have thought about it in a different way. But it's hard without knowing that from the outside. It's hard. You can't wake up in the morning and say, I'm going to think of things in a different way. That never quite works. It's never quite like that. You always follow nature in what it gives you, and then it's much more imaginative than we can ever be. And so that just rely on actually what nature provides you, and you'll be able to find a better solution.
Got someone over here who's been waiting.
Hello. I think my confusion was like a small dimensional part of what was just answered. Essentially, my understanding of what Einstein's theory about gravitational curvature says is that, like, if mass is moving in space, it's interacting with space and creating curvatures, which are essentially being communicated through gravitational waves. And if now gravitons themselves have a mass, wouldn't they also emanate their own sort of
Yes, absolutely. If gravitons have a mass, you can think, well, themselves, they lead to curvature. And that's true. But actually, the funny thing is, graviton or gravitational waves, irrespectively of whether they have a mass or not, they do lead to their own curvature as well, because it's not just mass that leads to curvature, it's anything at all. So if you have a gravitational wave, it's something physical. It's something there that carries energy. And so just its existence will lead to curvature. Now you can ask yourself, will the mass of the graviton lead to more curvature? And the mass is so small that that's not really what affects the amount of curvature that those gravitational waves carry, unless you go to very, very small frequency gravitational waves. So even the gravitational waves that have been observed, they may or may not have a mass, but they would lead to curvature. It's just their effect themselves is already so small. Seeing the effect of their curvature will be even smaller. Gravity is the smallest, is the weakest possible phenomenon that exists. So we're dealing with something which is doubly weak in some sense. Yeah.
Thank you.
Yeah, thank you. It's good to be the last, because it's not a question, it's more something I want to share with you, because you wanted to become an astronaut. Last year I met a European astronaut, a wonderful woman, Samantha. She speaks Italian, German, English, French, Russian, Chinese, and all that. So I was at a dinner with her, and I said, what's it like to be an astronaut? And she says, well, what's it like to be a professor? And I said, well, listen, I mean, you lived for 168 days without gravity. And she said, oh, gravity, that's a big mistake.
Actually, I wanted to ask you a last question. You work on gravity, but you like to go where no gravity is. I mean, underwater, sort of, and you'd like to go into space. So what is that about? Why?
I like to tease gravity, right? We like to challenge gravity. We like to play with it and understand and to get rid of it. I think that's exactly what you read earlier. Yeah, we can't.
Before the talk, we were having exactly this conversation about how it's. I had the same fascination.
You really?
You're probing the edges of it, and then you want to be without it, and yeah.
So if you could make yourself very small and go into water, would you?
Oh, yes.
I mean, then you could. Okay, just checking. This was wonderful. Thank you so much to both of you, and thank you for much. And
thank you.
I hope you'll join us for the cheese cubes, or maybe they're not cheese cubes today, and come and have your book signed if you'd like, or if you have more questions.